on the structured metric rank minimization. This is a joint work with Adams Yu, and my name is Wan Li. And to be more specific on what we mean by a structured matrix, actually we are working on so-called Hancock matrix. I'm going to give you a little background on why we use the rank of a Hancock matrix to represent the order of the system and why we have to minimize it. And after that, Adams will take care to give you some basic stuff of our algorithm and theoretical analysis. And at last, I will have some discussion on the challenges that we have when we're applying our algorithm. So the basic setup for our algorithm is in linear time invariant system. This is a system that is widely used in both signal processing and control theory. So given a system, we have a set of input called UT, and we have a set of output called YT. And the UT and YT are connected through a set of hidden variables, or what we call state variables, and called XT. And the dimension of XT, and in our settings called R, is order of the system. Usually, we prefer a system of low order, both for better analysis and for easier implementation. Okay, so usually when we want to model a system, we model a system by its impulse response. The impulse response means that you give the input is non-zero only at t equals 0, and you observe the output. And if we put out the impulse response in a way like this, we call it a Hancock matrix. The Hancock matrix actually means that all the lines crossing the diagonal is equal to each other, just like in the graph. And we can prove that any truncated block Hancock matrix, that means you take a submetric of this one, and the rank of this matrix will be bounded by the order of the system. So the first problem we're considering is called stochastic realization of an autoregressive moving average model. In this case, the input is just white noise, and the given signal is not the output, but we call it process covariance of the output. And we can form a optimization problem like this. Here we want the variable to be as close as our observed process covariance, and we want to minimize the rank of the matrix so that we can minimize the system order. And we can show that if we sample the Hancock, if we truncate the Hancock matrix with R elements that is greater than the true system order, and we can have the equation that the rank is equal to the system order exactly. And once we find this H, the coefficients can be recovered by the off-the-shelf method just in textbooks. So in our problems, it is commonly known that we can use a nuclear norm or trace norm of a matrix to be a convex surrogate of the rank of a matrix. And this is also the approach that we are using. Of course, there are some non-convex optimization problems to solve this problem, non-convex approaches to solve this problem, but given some previous literature, we know that the convex ones can work better. And to be more specific, the ADMI method on the primal algorithm, on the primal problem, outperform the other problem slightly. But we have to realize there is a significant problem in all this convex optimization problem. We can look at the algorithm here. For all the algorithms in each step, we have to do a SVD of the Hancock matrix. This can be prohibitively expensive because in SVD, the complexity is mn squared, which means you have to do a lot of work in each iteration. So our approach is trying to find another approach to solve this problem so that we can have a similar convergence rate, but for each iteration, we can significantly lower our calculation cost. And after this, Adam will give you how we form this problem using this one.
Okay, thanks, Wan Li. And now I will present our algorithm. So to make life easier, we first reformulate our problem. We introduce a new variable x to let it equals to the Hancock matrix. and let smaller x be the vectorized of this x matrix. And then we do the two transformation where bx equals to 0 and cx equals to y. Then we can find an equivalent formulation of the problem, which is this one. However, this is a constraint problem which is still hard to solve. So to make life more easier, we put this as a penalty term in our objective function. So after we arrange this term, we are minimizing this problem. And by rearranging this term, we let the objective to be the phi x, and we let the first two terms to be fx. Now we are ready to present our algorithm, which is called a generalized conditional gradient algorithm, or it is a Frank-Croft algorithm. It is adapted from Yao Liang's paper in NIPS 2012, and it's quite simple. And for each step, we find a direction which is similar to the Frank-Croft algorithm, and the step size is eta k, which is 2 over k plus 2. And then we do because we are aggressive, we want to make this each update make the objective decrease more faster. So we do this minimization and choose the theta. And then this is our update rule. The first term is the same as the Frank-Croft algorithm, and the second theta k is by solving this problem. Now we will show the property of this algorithm. The first thing is that when we find the direction, we avoid the SVD because we can see from this, we minimize this term is equivalent to maximize this term. And then what is this? It is nothing but the spectral norm of this gradient. So computing the spectral norm just needs to calculate the largest singular value. So it is much cheaper than do the full SVD. And the other thing is we minimize these functions in our algorithm. What is this? To take a look at this, one. Actually, this is an upper bound of the next step. So this term is by convexity, we can show that these two terms is larger than this term. And by the definition, zk is more than 1, so we relax this term. So this is the upper bound of this term. And finally, this is a projective function of theta, so we can find a closed form solution for this theta. So the computation is very cheap. Now we will show the convergence rate of our algorithm. It is also adapted from Yao Liang's paper, and we show that it is also 1 over k, which is the same as the state-of-the-art algorithm. Before proving this algorithm, we have such an assumption. It is this one. And it is a stronger version of the descent lemma of what we have learned in the lecture. That is, in this term, we have a constant. Not in the descent lemma, it should be the distance between these 2 points. Okay? Given this assumption, we are ready to prove this. So the first term is the objective function on the xk plus 1. And in the algorithm, we know that this is nothing but minimize the theta. Okay, this should be smaller or equal to. Because this the minimum, we just replace any value here. Replace theta with eta k times x star. X star is the optimal point. So by the assumption, we have this term. And by rearrange the terms, this line equals to this line. Okay, by the method we choose the direction, we can say that this is smaller than we choose an arbitrary y that obeys this. Okay? And then again, by the convexity of f, we know that this is smaller than this, just by convexity of f. And finally, we rearrange these terms to get this one. What is this term? It's nothing but the optimal objective value. So finally, we have phi on the x k plus 1 equals this one. After that, we rearrange our terms. We got this relation. And we know that the step size is 2 over k plus 2. Then by simple induction, we will have this rate. So what we have shown is that you know that 1 over k is equivalent to 1 over epsilon. So the overall complexity of algorithm is O mn over epsilon. And the state of the R algorithm, they achieve minimum, because this is the complexity of singular value decomposition, and which is qubit. So we are significantly faster than the state-of-the-art method. So let's show some preliminary results, which is the stochastic system realization problem. In this case, the linear operator is this, and the B is this. Okay, when this is the M equals to N, the M and N is the size of the Hankel matrix. So we can see that the overall running time, our algorithm is much faster than the singular value thresholding. And this is a case of much larger size. Okay, this is the third case. We can see that in all of the cases, our algorithm outperforms the state-of-the-art method. And one thing to be noted is that our algorithm is actually will be much faster because to compute this value, we do a singular value decomposition in our method just to plot this figure, and we do not exclude this time here. If we exclude this singular value decomposition, I believe that it would be much more faster. And another observation, very surprised, is that the convergence rate, this is the iteration, so this shows the convergence rate. The convergence rate is very fast. Theoretically, our convergence rate should be the same as the state-of-the-art algorithm. However, empirically, our algorithm is much faster in terms of convergence rate. So maybe due to the structure of the problem, we need to explore more after this presentation. So let's come.
Part I will give you some discussion on some challenges that I meet with this when we solve another problem. Here we can see the only difference is the rank is not only the Hankel matrix, but the Hankel matrix times another matrix. This is somehow makes the problem a little difficult because in the sub-problem, this constraint is no longer bounded. So, for conditional for Frank-Wolf, we have this each sub-problem will want our set, the domain to be bounded. And so in this case, I violate this constraints. And to make it more clear, we can divide the matrix into blocks. And we can see that in the algorithm that Adams has presented, we can calculate the gradient. We can calculate the z here by the leading the larger singular value decomposition of the gradient. However, here if we divide the matrix into blocks, we can update z2 by a similar approach because z2 is bounded. But there is no way we can update z1. Find a good way to find z1 for a similar setting. So this is a challenging problem that I encountered. So I welcome your any possible ideas. And a brief conclusion is that we use a generalized conditional gradient method, also called Frank-Wolf method to solve this structured low-rank approximation problem, and we lower the complexity per iteration from ONM squared to ONM by avoiding doing the full SVD. That's all. Thank you.
Okay, I'll ask a question. First of all, in your experiment, what is the rank of the matrix that you generated? The rank is very
10.
small, right?
10?
10.
Yes.
Okay. So
Yeah.
When you increase m and n, you did not increase the
Yes.
rank.
You do not.
The second question is I see that you have been doing something fancy in the Frank-Wolf algorithm. Instead of doing like the interpolation between the 2 points,
Yeah.
you are fixing like one half of the parameter and then doing a line search over the other parameter so that it's no longer a convex combination.
Yeah.
So how are you going to ensure that it's still within the constraint?
Well, actually, it's still a convex combination. We just use this to divide it by eta k. We just use our theta to decompose.
Can you go back to the
But
slide?
not from the formula on
Yeah.
pseudo-form.
This one?
Can you go back to the slide, the other algorithm block?
This
Yeah.
one, yeah.
Yeah,
Actually, we just use.
eta k there, and you use eta k on the other side. So
Yeah, actually, we just use this to divide it by. I mean, we can decompose this as eta k times such as alpha k, right? Alpha k.
So is that the algorithm that?
Yeah. So it is still a convex combination. Of course, actually, we do not do a constraint problem. There's no. This is unbounded problem. I mean, we are doing regularized.
I mean, the way it is written is not convex.
This is not a convex combination
It's
unless
a-
eta k equals to zero
Some
k.
convex combination. If 1 minus eta plus eta is less than equal to 1, but
Oh,
if 1 minus eta plus eta is bigger than 1, then it's not even sub-convex.
you mean that this might be larger than 1, or?
Is for a convex combination, the two coefficients should add up to 1.
Yeah,
Or
we can
if
use
it's
this.
equal to 1, you're still okay, but here, that's what Young is asking about. So Yu Chen is asking what is.
In our original derivation, we use this to do the alpha times eta k, right? So we can consider as the alpha k times zeta k as the point, and it's convex combination of alpha k, zk, and xk, right?
So eta k is eta k times alpha k times something.
Yes. So it's still a linear convex combination.
Okay, so it's a convex combination of xk and some other point.
And
Xk and sk.
alpha k times zk.
Okay.
Yeah. So actually, in Yang's paper, there is a more fancy way. They do the he also do the exploring here, and then he also has a more fancier way to accelerate this algorithm. We might need to do that after this presentation.
Actually, in the analysis, you use a descent lemma which has one minus eta and eta there. So if you use two different things, that's why I am just asking for you to clarify.
So, which?
Yeah, it doesn't matter. It's previous slides.
Previous
You
slides?
see, you have the 1 minus eta A and eta B, and this is a convex combination with a coefficient sum to 1.
Yeah.
So I believe you invoked this, and anyway.
So we use.
Okay.
Yeah. Here. Thanks.
Any other questions?
So I think you mentioned that the state of the art is one of the k field.
Well, most of them is 1 over k, but if we use the Nesterov accelerated, I think it should be 1 over k squared.
Yeah, why not? I mean, in this case, in the natural language and the usual language, the same scale complexity, and they both need one as the equation.
Yeah.
So why not try the natural language?
We do it in the future, but we believe that the n is the dominating factor. So if we want to solve the large scale problem, I think doing one SVD is very expensive, and even the Nestor method cannot do this. Yeah.
I mean, the dependency is better on epsilon, but
Yeah.
worse in terms of M and N.
Yes. Yes.
So
Yeah.
iteration complexity is better, but arithmetic complexity is not.
Yes. So the trade-off. Yeah.
But you should, I think, also mention that when means you've changed the problem a little bit, right?
Yeah, of course. Yeah. So
The matrix that comes out is not a truly Hankel matrix.
yes,
How
if
far it is from being Hankel, that is what you should also plot.
it is measured by this term. So if
So you should have really shown that,
Yeah.
because
we've
the
shown that
whole
this
problem is structured low rank approximation, and then there are two things that one should show there. Did you achieve lower rank? Well, you fixed the rank to be small, or did you actually get lower rank by tuning mu? Because many times actually trace norm does not really yield low rank.
Yeah.
It looks like science fiction, but it doesn't really yield low rank many
But
times.
since you are running on voiceless data,
Okay.
the underlying data is low rank. So
Okay,
it's
so-
like they
And the other thing is you're looking for structure, so it's good to show how well did you recover the structure. Because there are three components in your cost function, which are, two of those are constraints, but now they're the cost. But it's good to
just
show.
one is constraint.
Sure, means it's however you want to view it, but it's good to show that did you actually recover the structure you were trying to recover, right? It's like when I'm trying to learn, create a sparse model, it's good to report what level of did you actually recover it or not.
Okay. And maybe you can project the solution to this.
But the projection is non-trivial. You need to
Yeah.
alternatingly project to the low rank solution and also to this B
Yeah, so
constraint.
means that's the whole thing, because if you could just project, you will violate the rank probably.
Okay.
So it is important to see, means if lambda is big enough, then yes, you will probably satisfy Bx being small, which you probably have done experiments, but it's good to report those numbers, at least in the
Yeah.
final report you submit, you should show those numbers.
Yes. Actually, in our experiment, the norm would be 10 to the minus 4 or 10 to the minus 5.
Which is good, but report that.
Okay. Yeah.
Okay, I think we've already taken more time than